So let's see. First thing, in case anybody didn't get the word yet, labs have begun. So there's that. I got a couple of strange emails where people, I'm not sure that they understood that labs were actually a session that they had to go to. So, just mentioning that if those people happen to be here. And hopefully all is going well with that. And the final note, of course, there's always some issues the first week. Some of them are, beyond your control. Some of them are in your control. For example, on Tuesday, the UIC's virtual desktop platform was non-functional for a big chunk of the day. And, if the TAs start getting a lot of, stuff about that, or the professors do, we'll go in and we'll check and we'll say, oh yeah, you can't get in. So if the virtual desktop is off for a big chunk of the day, don't panic. It's not like you got to, stay up till, close to midnight just to make sure that you can try to get your stuff done. We're not that cruel because we can verify that it's not running. And the big thing is, if the lab session anyway, we're more forgiving about issues like that. Of course, if you didn't attend the lab session and then, yeah, virtual desktop was down, well, whatever, it is what it is. But anyway, the TAs know, and I've generally instructed them to be forgiving about these kind of first week of labs issues, even in cases where, it's the student's fault. I overslept, I forgot there were labs this week, whatever, my car hit a bus, something. But, in the appropriate cases, of course, first week problems happen, second week everybody should be on board doing things. We will be less forgiving. So there's that. Anyway, what we're going to do today, we're going to finish off the rest of this Facebook and access and security lecture. Time permitting, we'll dig into a little bit of the cases in there. If time does not permit, then I'll push them off till Tuesday. Again, Tuesday's primarily going to be a review session. If nobody has anything, I might go over a few of the cases just to give people a moment to think about stuff. But the review, the cases in there, there'll be a stretch of like 10 slides that cover various Facebook security issues over the last 10 years or so. Those are just to kind of be real world examples of some of the things we talk about as far as security threats. And so, they're not going to be directly testable. I'm not going to ask you, so explain what happened to Facebook in 2013 as far as, phony profiles. There won't be questions like that on the exam. It's just, again, talking about these security threats is sometimes a little bit abstract. It can help to have real cases. All right. So anyway, let's get on with it. Where we start is encryption, and I guess I need to start recording. I am recording, hooray. All right. So encryption is basically the process of you take data in its original form, which is called plain text, and you encrypt it somehow to make it unreadable. Sometimes that's called ciphertext, but anyway, so you take the plain text and you garble it up so that people who aren't supposed to look at it can't figure out what it's supposed to be. And then there's a mechanism for decrypting, for undoing the encryption so that its intended users can actually see it. Now, quite often, databases store sensitive data in some sort of scrambled, encrypted, or other form that's not easy for bad guys to find. For example, about 10 years ago, there was a big hack against eBay. Hackers basically got access to every eBay's account name and password. But fortunately for eBay, all of those passwords were scrambled. And as far as some of the usernames may have been scrambled as well, I'm not sure. But because everything was scrambled, then the bad guys, basically they had this block of data, untold gigs of data, that in theory contained all the username and password combinations. But in practice, unless they had centuries to apply all the world's computing power to solving this problem, it was pretty much useless. And the last I checked, they were trying to shop around this data set on the dark web for like $50 and had not yet found any takers because it was functionally kind of worthless. Now, having said that, quantum computers, they're on the horizon. They may be able to crack some of the existing security, from a few years ago. They may be able to do those computations faster. So if you do have an eBay account, maybe get around to changing your password by 2030 or so, because then it could be an issue. If quantum computing lives up to the hype, I guess we'll see. Same thing with the target attack. When I talked about the The hack on Target that led to having chips in the credit cards, same thing. Target had a big database full of user information. The hackers got to it, but fortunately, all of the passwords were encrypted, and so the bad guys couldn't really make any use of that for the same reason. Okay, so anyway, encryption, they take this plain text, they convert it to some scrambled gibberish along a fixed pattern using some standard algorithm, and the big point about it is it's reversible. Encryption would be an awful thing if you scrambled it and couldn't unscramble it to its original form. There is a related concept called hashing. Hashing is basically scrambling the data into groups. We'll talk about that in a bit too. But it's not necessarily reversible, doesn't necessarily have a one-to-one correspondence, right? So with encryption, if you have an input, you run it through the encryption algorithm, it's encrypted, you can undo that and it'll go to exactly what it was before. With hashing, potentially you can have a whole bunch of different inputs that lead to the same hash function output. And thus, if you try to do it in reverse, there's no guarantee that you would be able to figure out which one of those is the correct set of inputs that led to the result. So encryption is reversible, hashing probably not. Okay. So the encryption method we're going to talk about is something called asymmetric encryption. And this is out there, this is used. Last I checked, this is what Snapchat used. There's other websites that use it. There are other encryption mechanisms. Asymmetric encryption is certainly not the only one out there, but it's a neat one to talk about because it solves a core problem of communication. So imagine you have two people, Yvonne and Zoe, and they want to communicate through email, but they have to send messages over an open network. Open network meaning people can look in, read what they're sending. So they have to send data in some encrypted format, okay? So question, how can they encrypt their messages without fear of decryption by anybody, who can listen in on the conversation, either people that are eavesdropping in, or even if there's, hardware in the middle that retains copies of what they're sending, right? The different routers that the message goes through, whatever. Now, first of all, if Yvonne and Joey share a common encryption scheme, right? If they both have their separate code books and Yvonne writes the message in accordance with that code book and Zoe knows what the code book is and she can decrypt the message at the other end, then it's fine, right? And then it's like what they do on submarines, where every submarine has a code book, and they want to send out a message like, enemy sub northeast, and they have like a set of numbers that correspond to that message and they send it out. The other subs all know that because they all have the same code book, right? And assuming nobody else who's not a friendly sub, has that same code, nobody can decrypt the message. So that's fine. And it's fine for small groups of people, right? If Yvonne and Zoe want to have their own secret language, their own secret encryption algorithm, yeah, that's okay. Problem is that approach doesn't scale well. If you think about everybody on the internet working, trying to communicate, there's 10 billion different internet users, give or take, right? And that means you would have to develop 10 billion separate code schemes in order to communicate with everyone. Or at the very least, you'd have to develop a separate code scheme for every other person you talk to, every website you went to, things like that. So it'd be a huge hassle. You don't want to do that, right? You want to have some mechanism where you can send out messages encrypted and yet not have to create a unique set of communication encryption for every recipient. So that's the question. So how can Yvonne and Zoe exchange their keys, the ability to decrypt the information? How can they exchange those keys without a listener also obtaining them? That's the real trick, right? So for example, you go to a website, you would like to set up a secure connection with that website, say do credit card information, stuff like that. You need a secure way to send that. And it needs to be able to be done fairly quickly. Well, one way to do that is with what's called two-key encryption. So the core idea there is that Yvonne and Zoe each have two keys to lock and unlock messages. Now, what these keys actually are, the root issue is that they're big prime numbers. And big prime numbers have this neat feature where you can multiply them together. And when I say big, I mean like 40, 60, 80, 100-digit prime numbers, right? I mean big numbers. You can multiply those two numbers together on a computer very quickly. The math gets done in a microsecond, right? But factoring the product is very, very difficult. Because why? because there's only two factors in there. You have to, basically do a brute force search through all the different possible combinations in order to find out what the factors were. And even, at that, when the numbers are that big, there are that many possibilities. Basically, you have every computer on Earth working on this one problem for centuries in order to crack it. And even if, in theory, you can crack it, I mean, the electricity bill is not going to, be worth whatever data you're getting, right? If somebody's trying to crack my Facebook password, with that kind of encryption, it's going to cost a lot of money to, power every computer on Earth for centuries. So, and the contents of my Facebook account are really not worth the trouble. So, that's the core idea. You don't really have to, I'm not going to ask you about that on the exam, but it'll make a little bit of sense because what I'm going to mention now, the next thing, public and private keys. There are basically two numbers that you can use to multiply through the message. And these numbers, these keys, they have the property that one can undo the results of the other in both ways. So we have two big numbers. We're arbitrarily going to call them public and private keys. It doesn't matter which one you call public, doesn't matter which one you call private. But they have this property that any message you encrypt with a particular user's public key can be decrypted with that same user's private key. Any message that's been encrypted with a user's private key can be decrypted with that same user's public key, right? So it doesn't really matter which one is which. Anyway, in practice, the way this works, every network user shares their public key. They can plaster that all over the internet. It's not going to do any danger just by itself. Because why? Because the only message you can decrypt with that is something that's been encrypted with the user's private key. And the user keeps the private key private. You keep that on your own machine. You don't share with anyone. So if you want to send out a message, what you do is you encrypt it with the recipient's public key. You send that to them. The message can be encrypted using the recipient's private key, which presumably they and only they have. Okay? It's a neat system. The nice thing about it for large-scale use is it's easy to extend to a vast pool of users. So if you have n users, basically it's going to require 2n total keys, meaning each user has to come up with one pair of keys. But then once they have that, they can communicate with anybody. All they got to do to encrypt a message to send to someone, they get that user's public key, they encrypt it with the public key, the recipient can decrypt it with their own private key. If you're trying to do it with unique code pairs, you need n squared, right? Basically, you need a key for every user, but every user would need a key for every other user. So it becomes n squared, which means if you have 10 billion internet users, each user would need to generate 10 billion separate unique code systems. That would be a lot of work. Don't really want to do that much work for this. Okay. So that's what encryption is, why it's useful, okay? Now, how it's going to work. I'll do a picture for this because pictures are helpful, I hope. Okay. So, suppose Yvonne and Zoe want to exchange encrypted messages, okay, over an open network. So first, Yvonne wants to send a message to Zoe. She encrypts the message with Zoe's public key, right? Who can, what will allow decrypting this message? You shout it out, which can only be decrypted by Zoe's private key, right? If it was encrypted with Zoe's public key, what's going to decrypt it is Zoe's private key. So that's fine, because and only Zoe has Zoe's private key. So that's good. If Zoe wants to respond, she can encrypt the response with Yvonne's public key, which can only be decrypted by Yvonne's private key. And only Yvonne has Yvonne's private key, right? So this is good. You can send out messages securely once you have this pair of numbers. Yes. Last I checked, it's been a few years.
So when you're talking about keys, is that like choosing somebody to send a chat to?
Okay, well, when I say keys, the way to think about it is big prime numbers. Okay, I don't really want to get into the math of how all this works because number one, it's complicated, and number two, it's been like 10 years since I really thought about it and I've forgotten a lot. But like I said, the core concept is they're big prime numbers. When you do the math processing in the algorithm, the one can decrypt the other. Yeah, each person, right, whatever client stuff you install on your own machine, in your cookies on your machine, whatever, somewhere in there is your private key. Snapchat has the public key, makes it available to any user who wants to contact you. Yeah, so if you're sending a message you don't want anybody else to see, you encrypt it with that recipient's public key. Only the recipient can decrypt it. Yep. Anyway, it's a neat system. Okay. Yeah, I mean, if you wanna learn more about encryption, it is a neat topic, but you know, I am nothing like an expert, so not really my thing. But it is a very interesting topic. Now, following up on that, hashing. All right, so hashing is often used to solve a slightly different problem. So imagine that Yvonne wants to send a message to Zoe, and she knows it's going to be encrypted. It can't get messed up. But suppose she also knows her little brother Xerxes might tamper with it, right? Xerxes might be able to get in there and alter the contents of the message, even though he can't actually read what's in the message, okay? So a question, how can Zoe verify that any received message is in fact unchanged? Well, we have the hashing process. So what it's going to be, Yvonne runs the message through what's called a hash function that produces some output, some result. She sends the result along with her message. When Zoe receives the message, she runs the received message through the same hash function to verify that it produces the same result. And if it produces the same result, it's almost certain that the original message was not altered. I'll make a quick thing about that. So, yep, thank you. Okay, so suppose Yvonne wants to send Zoe a message and verify that Xerxes has not tampered with it. Okay, so Yvonne runs her message through a hash function. And let's suppose a hash function could be, you know, about anything. Let's suppose it's a sequence of additions and multiplications on each character in the message, and eventually results in some very large number. Okay, so at the end they run it through this hash function, whatever it is, we don't care, and it produces some very, very, very large number. Now, important thing, the hash sum only keeps the last, say, 18 digits. Okay, so whatever this final result is, it doesn't send along the whole big number. It just sends along like basically a checksum. See, you know, is the total right? Okay, and that gets attached along. So when Zoe receives the message plus the hash sum, she runs the message through the same function. If her result matches the hash sum that was sent, she can be almost certain that the message was not altered, right? Basically, 18 digits is 1 billion billion, so 1 in 1 billion chance of a random match. Okay, so first of all, most messages are not tampered with, right? Most of the time you send a message, it goes through, it's okay, there's no problem. Nobody tampers with them. But even on the off chance somebody does, it's still extremely unlikely that in this particular case that this hash sum would give you a different result, right? And there's nothing to say if you wanted to, you could keep like 36 digits or 99 digits, right? You could make it a pretty big string of numbers and have your, chances go from ridiculously small to, less than one in the lifetime of the universe chance of actually happening, right? You could make your probability arbitrarily small. So it's never gonna not be zero, but it could be so close to zero that, yeah, you're not gonna worry about it. Now, so that's one thing that you can do. And sending messages over networks, they generally do use this kind of checksum type approach. They total up all the data in the message, and there's a checksum associated with some segment of the message. And if the checksum matches, the chunk of data, then you figure, yeah, it's probably okay. Doesn't tell you where the error is, but if there was an error, the message could be resent. Also, where it's sometimes used, passwords, right? So, for example, if the site doesn't want to give away how long passwords are, what it could do is run the passwords themselves through a hash function and check at the end, does the hash result, of putting that password through match what's in the database. So database stores hash sums, passwords can be any format, right? So the hash sum, might be 1836 characters long, but the passwords maybe don't have to be that long. Or, the hash sum could be shorter. The password could be up to 20 characters, but the hash sum could be like, 10 or 12 characters, whatever. Anyway, but the point is, again, this is a way of storing passwords in a database without having to store them in an encrypted form. That basically, user enters in the password, the system runs that input password through the hash sum. Through the hash function, if the hash sum matches what's in the database, you say, yeah, is probably correct. Okay. Now, again, this isn't going to be the most super secure way to do this, but for a lot of systems, it might be secure enough. Okay. So anyway, yeah, hash functions are used in real life too. All right. So what do we have? Takeaways. Encryption and hashing, they're both potentially used for scrambling data. Encryption is with the explicit purpose of scrambling data. So, it takes, some original data, scrambles it to an output, then it's reversible. It can be restored to its original format. Hash functions, basically you take a potentially infinite range of data options and filter it down to one of a much smaller set of options. And again, where you might use it is checking if the message was received intact, or that's, or again, possibly for passwords. It has been used for that. Okay. Now, next thing for security, spam accounts. So spam accounts are these phony accounts. Typically why people nobody's going to create a spam account just for fun. I mean, I guess you could, but most of the time they're going to be created with some, devious, malicious purpose in mind. Sometimes people could use them as advertising tools, right? You could pretend to be a user who says, oh, I found this great new product. Or it could be a user who goes to a message board and, some, corporate Facebook page and starts liking on all the products and adds favorable comments in the, below and says, oh, I tried out this new vacuum cleaner. It's great. You should buy one. It's a bargain at $1,200. So they can be used for that. Like influencing public opinion, they can be used for that. Politicians or activists could create phony accounts to, add more activity to certain locations. Obviously, popular one, contact for criminal activity. So yeah, I've interacted with at least one spam account on Facebook. I don't remember the details. So it was a while ago. It was like 10, 15 years, probably closer to 15 years ago. There was somebody who offered to friend me. And at the time I was like, oh, maybe this is somebody who knows me or somebody who I met. I was in the Navy for 6 years in the 90s. This is maybe, somebody who I met that I don't remember. They remember me. Sure. So I accepted the friend request. She her profile said, you know, she was a Marine stationed in Iraq, and I was on a carrier, and we did have Marines on there, so it was not impossible. And I was naive, and I was like, okay, whatever. But then she starts pinging me, you know, instant messaging me, like, hey, what's up? Hey, you know, and I thought, ooh, this is kind of weird and sketchy, because I figured, you know, start a conversation with me first, right? You know, like, oh, hey, you're Doug, and I remember you from such and such. And I would be like, yeah, okay. But it was just weird. And it felt like phony, not a real person, whatever. And I figured, yeah, she's going to say she's in Iraq. She's going to say, I mean, she was saying, we should talk sometime. And, you know, I like your profile. We should talk sometime. And I know where that's going, right? I know it's going to, oh, I'm stationed in Iraq, and I think you're really neat, and I'd love to come see you when I'm on leave, but, you know, I don't have any money. I lost everything. I need $2,000 to buy plane tickets. And, yeah, you know how that shit goes. So I was like, yeah, I ditched her. But the other thing, gathering information about other users, right? If you're somebody significant, sometimes people create fake accounts to try to find out information about them so that they can use that for nefarious purposes, right? So, for example, there was a top admiral in NATO was being targeted for a while, that people were creating phony accounts of him or his friends in order to try to get information about his travel, in order to try to get information about him personally in case he was, you know, doing something dumb like using his wife's birthday for, you know, a PIN code, something like that. Anyway, yeah, they were trying to do that as part of an espionage activity. Anyway, so symptoms of spam account. Well, I'm gonna bring this up. I'm gonna go back to Facebook here. Screen, I know. This is the same one I brought up before for my other class. So you can see my Facebook page. I have one. Okay. Facebook, where am I? I go to home. No, I go to Doug. I'm already at home. I go to Doug. I look at my friends, requests. Okay, so here, you know, like I said, you can imagine, right? These are the fake ones mostly. Anyone that I don't have mutual friends with, right? So here's one. She's cute, whichever one she is. I'm not sure. I guess she's the blonde one. You know, if I were 30 years younger, I'd be interested. I'd say, hey, what's happening, right? But she's not. Let's see. Her last posts were in 2013. Somehow she has 60 friends, though. That's interesting. Probably her friends are fake-ass friends that also are not real people. Or there's, you know, sadly desperate people, whatever. She has, you know what, 6 actual photos. And she is cute, whatever. But all her other stuff is test and keep an iPad free. That's kind of questionable, right? I don't think there's any iPad there. Yeah. Anyway, so you get the idea. What are the symptoms of a spam account? Well, number one, there's practically no information, no posts, no photos. It's a very thin account, right? Over 10 years, if she was a real person, you'd think she'd have put a little more stuff in there or deleted her account, right? Number two, negligible interaction with friends, right? Most people, they go on Facebook. Once in a while, they'll message somebody. Once in a while, they'll make a post. Once in a while, they'll like something somebody does. Number three, single dominant activity type. So for example, if you are a spam account created for advertising tool, mostly what you're going to do is go to a few particular, you know, business Facebook pages and do the same kind of actions on them, right? And last, burst of friend requests. Normal Facebook account, if you're a human, you join, there's like a window of the first week, you see people you like that you know, you send them friend requests, other people recognize you, say, oh, you know, Doug's on Facebook now, okay, I'll send him a friend request. There's a little bit of back and forth there, and it kind of tapers down after the first month, right? That's how it is. But if it's a fake account, you're going to have this burst of friend requests, right? You send out a whole bunch when you first arrive on Facebook. You probably never get any friend requests back, right? Because you're not even a real person. Who's going to care that you're on there? And then, you know, it probably you don't do anymore for a while. Or maybe there's another big burst. If you're a scammer, right, periodically you say, oh, I'm not getting any traction with the spam account. I'm going to send out another few hundred friend requests and see what happens with that. All right, so they're kind of easy to recognize if they're basic ones. But you might ask, well, how do these even survive, right? You can see that some of the one, you know, that one was almost 10 years old. I have other ones in there that are very old. Well, the way Facebook detects them, it's a lot like mailbox spam detection. First of all, it builds some profile of normal behavior, right, or what a normal message looks like, and then it identifies deviations from that. So basically what they're doing, if you want to look at it mathematical form, let's suppose this line represents normal, average Facebook user behavior, okay? However they're generating that line, they're going to format it into some kind of line, okay? If you're fairly close to that, like you're in these bounds, right, then they're going to look at that and say, okay, probably legit user, right? But if you're on the outside, probably spam account, right? And same thing on this side, probably a spam account. Now, of course, this isn't a perfect thing, right? You could be some user who just has really weird behavior profile. And you might, you know, even though you're a legit human, you know, Facebook might look at you and say, wow, you're not on that much. You send out weird random friend requests to people you don't know, and you spend most of your time giving likes to vacuum cleaner manufacturers. You're weird, but you're still an actual human. Likewise, it's conceivable that you could be a fake account, but act like a normal user, right? One of the things you read about these various money scams that often target lonely older women, right? And they say, hey, I saw your profile. Your pictures are really cute. My name's Bob, and I'd like to get to know you better. And they start talking and talking for a couple months. And then Bob runs into money problems. Oh, Bob's going to get evicted. Or Bob would really love to come see you, but gosh, I just had these medical problems and I can't afford the tickets right now. But you know what? If you Venmo me a couple $1,000s, yeah, that'd be great. And I'll meet you at the airport, right? And you read about these things and it's like, wow, how do people fall for this stuff? But they do. And anyway, that sort of scammy effort definitely takes a lot of time, right? It's not like that's going to be just some simple bot algorithm controlling that. There's an actual user behind the spam account. It's just a fake account, right? But he's generating, you know, all these messages and pretending to be a real person. Facebook's not really going to get that. So the system isn't perfect. The system kind of can't be perfect, but that's what they try. Now, again, another thing there is besides just Facebook's math is flagging by users. If some user notices the account and says, yeah, this is fake, there's a pretty good chance Facebook's going to look at it and agree and say, yeah, this is fake, can it? Now, I could do that with those fake, you know, spam accounts that send me friend requests, but I find them useful for my lectures, so I don't. Yeah. But anyway, some false positives and negatives are inevitable. The system isn't perfect. So how do they survive? Well, number one, operating at small scale, right? If it's a small account that only has a few friends and isn't really doing anything, look, Facebook can still count that up as one of the people who's logged into Facebook. They're not really in a big rush to get rid of every account, especially small ones that aren't really bothering anybody. Number two, even if the bad guys do get their accounts canceled, they can just get a new email address and make a new one, right? It's not that hard to do. Three, in some cases, the accounts have gotten more sophisticated and actually mimic, you know, more natural user behaviors. You know, you might write scripts that has them generate fake posts or, you know, go on Facebook and play Candy Crush or something. You know, you might do that if you really wanted to make your account seem credible. Anyway, the arms race never ends. The bad guys are out creating spam accounts. Facebook is trying to cut down on the worst ones. But again, if they're small and they're not doing much damage, Facebook kind of doesn't care because clearly it's letting all those spam accounts persist. And this goes more generally to the concept of security versus usability. So when I say some false positives and negatives are inevitable, Facebook really doesn't want to accidentally cancel a valid user account just because it looks weird, right? Unless it's actually harming people or they get complaints about it, Facebook's kind of live and let live because the account might be real. And this is, like I said, this is kind of a trade-off between security and usability. So perfect security is impossible. That was the dogma we pretty much started the lecture off with the other day. So managers have to balance usability against security. Basically, all the hoops you make users jump through is going to be a hassle, and in some way it's going to impose costs. It's going to impose costs, maybe reducing employee productivity in the terms of Facebook. Maybe it's going to lead to users abandoning Facebook and going somewhere else, or just using Facebook less. You know, so there is this kind of trade-off. And what you don't want to do is maximize your usability, right? You don't want to minimize your usability costs, because that'll mean your security will be weak. Likewise, you don't want to maximize your security, because that will impose more usability costs. The more security you have, you know, eventually it's going to start inconveniencing users. So what you want to do is hit that kind of balance where you minimize the sum of the two. You have to recognize that security imposes costs just as security failures impose costs. And you want to, you know, minimize the sum there. So, for example, we'll talk about how system users might respond to excessive security requirements. So back when, there was a woman at Champaign-Urbana that this was her whole field of research. This, you know, basically looking at security and how workers respond to security features that are too demanding. So, suppose you are a good and loyal employee and you want to follow your business directives, okay? And your employer has decided to impose stricter security and require daily password changes. Holy shit, why the fuck would they do that? Yeah, that's a lot of work, right? That's gonna be a hassle. Okay, but that's what they've done, right? Somewhere in the system, they got the idea, you know what? You're gonna change your password every day. And you're a good and loyal employee, so you're not gonna just leave, and you're not gonna find some way to not change your password every day. You actually are going to change your password every day. But what might you do to minimize the hassle for yourself? Yeah, single character change, right? Minimal single character change. Right? Like 1, 2, 3, 4, etc. at the password end. And lots of people do that, right? And systems have kind of caught on, and they say basically, yeah, you can't have a password, you know, end with the same digits. What's an extreme case of that? What's an extreme case of minimal password changing? Only keeping 2 passwords and swapping every day, right? So day 1, you use password X, day 2, you use password Y, day 3, you go back to password X. You only have to know 2 passwords, right? So again, this meets the letter of the requirement. You're doing the password change, but you're not nearly achieving, you know, the security outcomes that the business thinks they're going to get. So the business sees employees are doing this, and they say, you must use a completely new and random password every day, right? No more of this single character change. And you're still a loyal employee, so you're going to comply with the letter of this. But how might you respond? Well, first of all, what problem will likely arise? And what happens when people forget passwords? They what? Yes, so lockouts, lost productivity, right? Because if they're locked out of the system, they can't do it. It takes longer to get in. What else? More help desk time, right? Yeah, so all that stuff. So that's going to be bad. What else? How will employees likely respond to make their own lives easier? What would you do if you had to create a new and random password every day and you weren't a robot and you had trouble remembering it? Well, you can't recycle it because they check. But yeah, write them down. Write them down either on paper or in like an MS Word file, right? Something like that, which, by the way, which creates security risks, duh, right? What else might you do? Well, you might download massive batches of data to avoid needing to log in, right? You might say, wow, this system is a hassle, but guess what? If I don't ever log in, I don't need to remember the new password. Aha, I'm just gonna like download 50 gigs of data like once a month and then not really work within the system. That might be possible depending on how it's set up. Or if you are an IT employee, you might devise a backdoor into the system and, you know, have some easy to remember stable password like admin plus password, right? You might do something like that, which again creates massive security risks. But these are the sort of things that happen in real life, right? If the system becomes too much of a hassle to use, people are going to find workarounds. They're going to say, well, I still got to get my work done. My manager, he doesn't care that I got password troubles, you know? So the consequence of all this, adding new security features and requirements does not absolutely guarantee that you'll have real better security. Because why? Because people aren't robots, right? People are not always going to respond in the way that you think they might. All right. Now, next stuff, whole bunch of different security threats. And actually, we're doing pretty well time-wise, so I think we should have time to go over some cases. So, in this, we'll cover some of the very common types of security threats. And then afterwards, we'll talk about some of these Facebook security breaches. And then there'll be a little bit left of some practical workplace information. So, first one is the brute force, there we go, the brute force attack. So in computer science terms, a brute force algorithm is an algorithm that considers every possibility. And by considering every possibility to a problem, it absolutely will eventually get the correct answer. For example, suppose I tell you, I'm thinking of a random number between 1 and a trillion. Well, given a trillion guesses for every possible number, you will eventually guess it, right? That's what a brute force algorithm is. It's not generally very efficient, but it will solve the problem. So, like I said, brute force attack on passwords, yes, it will work eventually. Problem is, if the password is sufficiently complex, right, many characters, many options, eventually it could be a really, really, really long time. And what does that mean? Well, what it could mean is that the electricity bill will probably cost way more than the value of any data you might get. Okay, so brute force attempts these days take a long time. But there was, again, passwords used to be simpler. And for example, like Social Security Administration, they have an absurdly simple password setup because, you know, it's a government thing and, you know, government's always the last shit to get updated. You have like set up an 8-letter password. Maybe they use numbers too, but I think it was literally 8 letters last I checked. And there's not going to be that many possibilities. So that kind of password, right? Let's see, 676, about 40,000. What's 40,000 squared? That's going to be 1,600 million, 1.6 billion. If you have a fast connection, you could conceivably do that. You could crack that account in a reasonable amount of time if you didn't get locked out. So, yeah, Social Security Administration, beware. Anyway, but yeah, if it's something like Facebook, you know, where there are like many characters, up to like 12, 16 characters and like 100 options for each one, then it's exponentially harder to crack with brute force. So, practical solution to brute force, number one, strong passwords. If your password is long and has a lot of oddball characters in it, it's going to take a long time to crack. And better yet, enforce delays or locking the account after 3 or 5 failed login attempts, right? So, you know, it's, again, there's not going to be a 0 probability that a brute force attack could work, but it's really, 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 really unlikely, okay? And in a well-designed system, simply brute force attacks are not a severe threat. Bad guys aren't even going to bother doing it because why? Because the electricity bill isn't going to be worth the effort. All right. However, Guessing and stealing, those are possible under the right circumstances. So guessing passwords, again, if you have a random oddball password, sure, you're not going to guess that in practice. But if you have a password that includes personal data, like names or birthdays of spouse or children, that's guessable. If it includes common words here, somehow I'm missing a parenthesis there. That shouldn't happen. Okay. Or includes common words. They can do a dictionary attack like I talked about. How else? Stealing, right? Stealing is more of a viable attempt. So if you're in a wireless situation and you have to transmit your password, it's possible that bad guys could grab a character sequence out of that, especially if the password is transmitted in the clear instead of encrypted. You can also have keystroke logging, right? That can be done with malware, or it could be done with actual hardware attached to a machine in a public place. The stuff exists to track keywords, to track keystrokes. So you can look at somebody types in their type username, hits tab to move to the next block, types in their password, and then hits enter to log into the system. Well, guess what? Whatever's between that tab and that enter key press, that's probably the password, and bad guys can figure that out. If your browser has passwords locally stored, potentially malware could get in there and access those. Of course, identical passwords from insecure sites, right? It might be that Facebook is storing your password very securely, but you use the same password on some other junky website that isn't concerned at all about security and is just storing passwords as plain text in some database that's fairly easy to hack. So guess what? The hackers get that one. They see your email is affiliated with it. They say, yeah, he's probably using the same email as a Facebook account, so they check that same username, password on Facebook. They check it on all the major banking operations. They check it on Gmail. They check it on Target, Walmart, Bank of America, whatever, right? Maybe you're using it on a whole bunch of sites. And last, of course, phishing. Phishing tends to happen because guessing is hard, brute force attacks are hard, even stealing is pretty hard. But phishing is cheap and easy to do. You can send out 1 million phishing emails and you'll get some people. Pretty easy to do. All right, so phishing is one of the most popular, most successful methods for obtaining access credentials. And I'm sure you guys have all heard of phishing. You have an idea of what it is, but we'll talk more. So in essence with phishing, users gets duped into giving up their ID and password, typically to some kind of phony site. So typical attack method for phishing, number one, send an email advising the reader that some problem requires immediate password change and you got to log into a site immediately to do it. Or some cases, you send an email with a malware attachment. You say, hey, Bob, I just got your thing about the meeting the other day, and here's the spreadsheet. Take a look at this. And when they open it, an Excel file, but it has some malware somehow attached, and they get infected. Okay. Now, those of you who have older relatives, you may have received calls about phishing attacks. I remember it was about 15 years ago. My mom, who is very old now, but was still old 15 years ago, and she wasn't computer illiterate. She'd been working with computers since like the 80s. And she had email before I did. So she was in no way computer illiterate, but she calls me up in a panic one day and she says, Doug, I got a big problem. And I'm thinking it's some health issue, maybe my dad got a heart attack or something. But no, I'm like, okay, Mom, what's the problem? And she's like, well, I just got a notification from Bank of America that my account has been hacked. And I said, well, that's not good. And she said, yeah, and they want me to go to their secure server and, update my password so nobody can get in. And I was like, oh, that seems reasonable. And she said, but Doug, I don't have an account at Bank of America. And I said, okay, Mom, this is what's called phishing, and somebody's trying to scam you. But since you don't have a Bank of America account, there's not really any damage they can do. You're okay. Everything's cool. Anyway, some of you may get, frantic calls like that from some of your older relatives one day if you haven't already. But that's the kind of thing, right? So generally the email will have some kind of personalized link attached that says, hey, here's where you go to do this, right? And then when the reader goes there, they visit the site, they enter in their user ID and their password, and they've given away the keys. Okay, now for phishing, preserving the illusion of legitimacy is vital. The big reason for that is there's typically a very long delay before any real damage happens. What usually is the case is the people doing the phishing are not the ones that are actually going to use the information, right? They send out like 10,000 or 1,000,000 emails. They get a few, bytes with each batch. Eventually, they'll have enough to bundle it in some standard scam package and sell it on the dark net. They say, here's a bundle of 1,000 Facebook access credentials, for $100, right? Or here's 10,000 for $500, whatever, right? So they want to get a certain batch so they can sell it as a bundle, and that'll be that. Now, it takes a while, right? It takes them a while to build up that many, account credentials to make the bundle they want to get. And then they have to put it on the dark web. It's going to take a little while to sell it. So what you don't want is somebody saying afterwards, you know what? I went and changed my password, but something about that whole situation seemed a little fishy. I better go and change my password again, right? They don't want people to think like that. So accordingly, phishers might use a phony but plausible email source address. They might use a phony site with a similar URL, like swapping out a capital I for a lowercase l or vice versa. They might reorder or merge terms. For example, if Target has a legitimate subsite called help.target.com, you might create some phony site called targethelp.com that at least sounds good, right? And what they very often do is if you go to the phishing site and you give away your user ID and password, they have some back-end process where they actually contact the real site, update your password there, and then they redirect you to the site. So for example, you get a scam saying, hey, your Target account has been compromised. Please update your password. You go to the scammer's site, enter in your username and password, and say, enter in your username, your password, old password, enter in your new password. Then they'll take that information, create the new password, update it at Target for you, and then they'll helpfully redirect you to Target already logged in. They'll say, thank you, great, your account is totally secure now, we're resending you to Target. And people who are naive enough to click on the link and go and give away their password, they're going to think, oh yeah, here I am at Target. How could they have redirected me to Target if they weren't legit? Right? So yeah. Anyway, spoofing is another thing that's commonly used. You try to misrepresent who you are in the email sender block, or you have a link appear as something different than it is. So spoofing is misrepresenting a name, like an internet address, website name, email address, whatever. It's not inherently a bad thing. I'll show you why. I'm going to go to one of these online web editors. It's a feature that's built in for a very practical purpose. It's built into HTML. Oh gosh, Katie. We could, good times we could have had together if you were just a real person. Oh well. Anyway, so there's a site called W3 Schools, and they have a try it yourself, right? You can put in code on this. So I'm going to go there, the try it editor. So here I'm going to put in a link. I'm going to put in the link. I'll change the header here to UIC. I'm going to put in a hyperlink for href is where the link actually leads to. So https www.uic.edu, and then UIC. Okay, so when I do this, this creates a link, UIC. It doesn't actually contain the text www.uic.edu, but when I click on it, it directs me to the UIC website, which is fine, right? It's a perfectly sensible thing to do. You'd like to have a slightly different bit of text, you could put in something like, click here to learn more about UIC. But where it becomes a problem, right, is if you edit it and say, for example, Google it. You think, well, a lot of people are going to use Google. I'll click on that. But instead, UIC is trying to steal traffic that should be going to Google, and they want to advertise UIC, right? That's where it's, kind of trying to deceive somebody. That's where spoofing becomes a problem. So like I said, spoofing isn't inherently a bad thing. It's something that gets used widely on the internet for totally fine purposes, but it's also something that bad guys use. Okay. Anyway, so phishing naturally is going to use spoofing because it wants, users to trust the message, right? Now, a lot of phishing attempts are really garbage, right? You look at them, the fonts are sloppy. They don't include images like legit corporate emails would. There's misspellings throughout, Yeah, you just look at that and you say, wow, you guys really are not trying. And the other thing, hovering the cursor over a link in an email most email systems should create a pop-up the actual link. So, you know, if it says something like log into our secure server, target.com, and you hover over it and you can tell it's like directing you to something in North Korea, then you'd be like, yeah, this looks a little fishy, I'm gonna do it. Okay, so ordinary phishing, that's how that works. Now, phishing typically casts a very wide net. So think about if you're one of those ocean fishing operations, you got a big ship, you drag a big net behind you, you try to catch some fish, right? You don't really care which fish you get. You're out there fishing for tuna. You don't care if you catch Charlie the tuna or Fred the tuna. It doesn't matter. You just want to catch some fish, right? It's a numbers game. You do a large volume of attacks to get a few hits. However, spear phishing targets important people, right? And the example I use, Moby Dick, right? The white whale. The dude who was going after the white whale really wanted that one whale. There were lots of other whales out there, but he wanted that one. So spear phishing, again, you have a particular target in mind. And there's lots of reasons why different targets might get done. So for example, the DNC hack 2016, spear phishing there, right? They really wanted to get that guy's access credentials so they could, you know, figure out what all, you know, information he had and publish it as dirt, that sort of thing. There was another one a few years ago. There was that movie about the North Korean dictator called The Interview. Yeah, and North Korea did not think that was very funny because it was kind of about assassinating him. So, you know, they tried to put pressure on Sony to not release the movie. They hacked Sony's email accounts, their top executives' email accounts, and published whatever embarrassing stuff they could find, right? So again, very clearly targeted. Now, the way this often works is with something called a multi-stage attack. So if you get an email that has some random unknown source, somebody you don't know, you're going to look at that and say, oh, this is spam, this is garbage, this is malware, I'm not going to open it, right? We all have enough sense to do that. Right? If you have no idea who the email is from and it looks scammy, you're like, yeah, no thanks. However, what if it came from your own IT department with a legitimate email source? You know, this is Bob from your security team. Yeah, chances are you'd open it, right? So this is what multi-stage attacks do. First of all, they try to acquire credentials of some IT security employees, typically by phishing. So they might, you know, because even security people can make mistakes. They can say, oh, you know, the phishing attack says, hey, I see that you're in security on there. Here's a PDF containing information on some of our new security products you might be interested in. Well, when they open up the PDF, it has some clever new vulnerability that's not going to get detected. They get infected, the bad guys get their access credentials. Once the bad guys have the security team's access credentials, they can send out emails from the security employee's account. They can send it up to top executives. They can say, hey, this is Bob from security. Please let, you know, Susie, the CEO, know that it's time to change her password. And Susie's executive assistant isn't really going to question it. She's going to say, yeah, okay, I'll do that. So she goes and she updates the password, and boom. The bad guys get elevated access levels, you know, to whatever, you know, their intended target has. Afterwards, the plan is typically to gather as much relevant data as they want and exfiltrate it. Exfiltrate is a security term, basically meaning to get the data out of the organization. X for get it out, I guess filtrate for getting it past the security defenses. And typically it gets sent to some kind of anonymous file sharing services. In the Sony attack, for example, all the data went to one file shape. They had it already bundled into like DVD-sized packets, chunks. They sent that to one file sharing service. They had that file sharing service echo it to a new file sharing service, and that one echo it to another. Went through a chain of like 10 or 15 different file sharing services, so it was very difficult to trace where it came from. But funny follow-up to that, I don't know if you guys know, the North Korea being a very isolated and secretive country, basically they have essentially one internet connection to the outside world. And you know, the US's security team, they decided they were actually just gonna basically do a denial of service attack and shut down that one gateway for like a few days. So yeah, anyway, that was kind of the reaction. Okay, which brings us to denial of service attacks. So a denial of service attack is simply an attempt to overload a network by sending in more connection requests than the network can process and making legitimate connection requests not have time to go through. Okay, so basically it forces the network to respond to lots of repeated small communications. Now, if the attack only comes from one machine, it's pretty easy to block. Back in the day, actually, you could do this on America Online. They had little chat rooms in America Online, and one of the most common tools for ruining people's day was you could have a thing that would send them the ping of death. Basically, it was something that took so long for your system to reply to, to respond to, that your system became inactivated for an extended length of time, and AOL thought you timed out, and it dropped you from the system. So if you were in a chat room and you were being annoying, somebody could hit you with the ping of death, and your account would freeze, and then you'd get dropped from AOL and you'd have to log back in. Kind of the same idea. But again, from a single attack, it's pretty easy to block. The network administrators can say, oh, yeah, we're getting an annoying overload of, connection requests from this one source. We're going to block it, right? Chances are there's like automated protections built into the network to do just that. But if there's a whole bunch of simultaneous requests and from thousands or millions of different machines, that's a lot harder to deal with, right? It's because it's not the same as a million requests from one machine. You can easily stop and block that. If there are a million machines, you don't know which of them are legit connection requests and which ones aren't. So problem is, that's called a distributed denial of service attack, because the attack is distributed over many machines. But the thing is, that kind of attack is much too large to be controlled manually. And eventually, the network administrators can figure out which machines are legitimate users, which ones aren't, block the illegitimate users, and eventually, restore the system to normal operating patterns. But it's still going to ruin their day. So a denial of service attack, it's not permanent, it can be resolved, but it is going to take time, and we all know time is money. So the big companies, they don't want this sort of stuff to happen. So it's often done as a threat. Bad guys will say, if you're doing some stuff we don't like, we'll do a denial of service attack on you if you don't stop. Okay, another one is SQL injection. So SQL injection, mostly obsolete. What it does, it essentially tries to put active SQL code in the password verification process. So remember, SQL, language of databases. This was widely possible about 20 years ago. There were a lot of places you could get away with this. Now, pretty much any sensible website is going to have blocked executable SQL code. So the way it normally works, the way the database check normally works, you'll have some SQL command like select star, that's a wildcard, from the table users where the name field equals whatever name has been entered, and the password field equals whatever the password has been entered, right? And if the name matches one name in the database, well, the name is presumably a key field, and there's only one name that matches that. And therefore, if the password matches, they'll send you access credentials, and if the password doesn't match, they'll say, sorry, try again. But in the SQL injection attack, what happens is you change what's put in the password to change the actual SQL command in the database. So then, if you put in what's in red there, it'll be select star from the table users where the name field matches the name you put in. And this is a logical OR statement at the end, where either the password is an empty zero-length text string, which is not going to be true, or the character 1 is equal to the character 1. Well, guess what? The character 1 is always going to be equal to the character 1. They're the same character. So that part of it is always going to be true. So that logical OR statement is going to resolve as true. So the name's going to match the name in the database that you entered, and you will automatically get the access credentials for that user. Okay, so SQL injection attacks were pretty devastating when they were possible. Another one, cross-site scripting. So the basic idea with cross-site scripting, although there's a lot of different flavors on it, but the basic idea is you put in some scripting code into a page that wasn't supposed to be there, and it does something bad. So it's similar to the SQL injection attack, but uses JavaScript on web pages. So when the web page runs, right, when your browser looks at the web page, it's going to see that script that was put in there, and it's going to execute it as active code, which can do any number of bad things. I'm going to give a simple example. Now, it's not possible on Facebook anymore. Facebook is obviously wise to this particular thing. I guess we don't really have time to go on talk about security, but we'll talk about some stuff for sure. All right, so I'm going to do my usual summer thing. Sounds like a big party next door, huh? Yeah. Okay, so we're gonna have our summer picture in just a moment here. Okay, so you post some picture on Facebook, right? And user one responds, wow, looks fun. User two, wish I was there. User three, script, inject malware, and script, right? And what'll happen is if the website isn't careful about this shit, what'll happen is that script will actually execute because of the way HTML is structured. You can have scripts nested within other HTML tags. So yeah, this was one simple type of cross-site scripting attack. Anyway, so normally I'd spend a little time, but I guess we're right at the end. So I got a few things. I'm gonna grind out the last stuff, the last few slides. So don't worry, these will go quick. So question number one, who are the attackers? Well, a lot of them are government agencies, military or espionage groups. The big chunk of them is actually criminal organizations. They're looking to make money in various ways. And there are a few lone oddballs out there doing this sort of thing too. So we can ask, why do they launch attacks? Well, in most cases, to steal intrinsically valuable information, right? Espionage services, they want to steal state secrets. Military organizations, they want to learn about, military secrets that the other side has. Criminals, they want to get money, right? They'll steal bank account information. They might also do blackmail. If you, for example, don't like what some service is doing, like, for example, North Korea with Sony, they didn't like that movie, so they said, if you that movie, we'll release all your emails. Ransomware attacks are quite common. They're often launched against municipalities, and it'll be something like, you got to give us 10 grand or $1 million in Bitcoin for us to give you the key to restore your systems. Actually, a few years ago, the UK's National Health Service got hit with a massive ransomware attack like that. Sometimes to restore, influence policy, right? Cite up, I don't know. What asshole would call me during lecture? Yeah. That call is a Kiwi bird call, and it is very loud, and I do not miss many calls anymore. Of course, you can also have personal motives, right? You could be some disgruntled security employee. You're like, you didn't take me seriously while I was here. Well, I'll show you have a lot of vulnerabilities. Now, aggregate damage, you'll see a lot of different numbers. So the first one, about 7 billion annually in the US, that's actually damages caused by security attacks. If you start looking at the total cost of attacks and prevention is huge, right? All the software that people install, all the security employees, that number gets big. They list that as about $1 trillion. But it might be a lot bigger. Here you have another one that says it's closer to 6 trillion. So again, how do these numbers get so different? Well, number one, different organizations are going to push different viewpoints. So for example, that 6 trillion number, if you look at who's posting it, it's cybersecurityventures.com. They're selling security services. Of course they want to give you the biggest, most alarming number possible. And in many cases, methodology differences. Methodology, research term for how you do it, okay? So if they're looking at different things, or they're looking at the same things in different ways, yeah, they're going to get different numbers. Now, organizational security, most security failures are due, at least in some part, to employee failures. Employees doing things they shouldn't, right? Going to a website they shouldn't, failing to install security software, opening an email or an attachment, and stuff like that. So they need regular training, clear policies should exist, but beyond that, the business always has to monitor system activity, right? And do periodic risk assessments. But again, the big weak point is usually employees doing things they shouldn't. So as far as individual security, here's things you can do to avoid, losing your job for being part of a security failure. Number one, don't install unauthorized software, right? If the organization says, yeah, don't install a password manager because we know that that could be cracked somehow, yeah, don't install it. Keep your passwords strong. Keep antivirus tools active, even if they're slowing down what you try to do. Don't turn them off so that you can do your web browsing faster. Any security updates that come along, install them right away, right? Don't disable your Windows security and say, I don't want to get any security updates for a month because, again, it's interfering with my browsing. Be aware of suspicious email. open them. If you do have any important documents, regularly back them up and store them in the cloud somewhere. So if you get hit by ransomware, it's not going to ruin your life. And if you have legit security concerns, forward them to your organization's security contact. For example, suppose you just updated your password and then you get a notification that appears to be from your organization's security team, and they say, hey, it's time for you to update your password. Please log into our secure server. You'd be like, huh, that's weird. I just updated it. Talk to your security people, right? Be part of the solution, not the problem. Okay, that's all I got. Tuesday is the review session. I'll see you all then. Have a good weekend.